Section 3.6 is derivatives of inverse functions. I am going to let you know that I did not do exactly what the e-text did in this chapter, in this section. The e-text goes a little deeper, starts using compositions of functions being inverse functions and having you evaluate it at different points, and it's way more confusing than it wanted to be. I wasn't going to cover stuff that I wasn't going to test you on, so I wanted to get straight to it. Really what we're looking at here is looking at our derivatives of inverse trig functions. The ones that I want you to concentrate on are sine, cosine, and tangent, meaning the derivatives of the inverse sine, called arc sine in our textbook, inverse cosine, which would be called arc cosine, and inverse tangent would be called arc cotangent. We're going to see the ones for arc secant and arc cosecant. You will have to memorize them, you will have to be able to use them, but I want you to see how can we derive those formulas. Now, we honestly already kind of did this in one of the previous sections. So let's look at this. What we started off with in the previous section was we started off with trying to find the derivative of sine of y equals x. And so what we did was implicit differentiation of both sides. We took the derivative of both sides. The derivative of sine of y is cosine of y prime, and the derivative of x was 1. And then we ended up with y prime, divide both sides by cosine of y, right? We ended up with y prime equals 1 over cosine of y. Well, in section 3.5, I said that was enough for the implicit differentiation section. But then what I also did was I showed you the proof that we could actually substitute in for cosine of y. And the way that we did that is we used the fact that sine squared plus sine squared of, it doesn't matter what it is, sine squared of y plus cosine squared of y equals 1, right? And so we subtracted sine of y from both sides, so we said cosine squared of y equals 1 minus sine squared of y. And then we took the square root of both sides, and we said that cosine of y has to equal the square root of 1 minus sine squared of y. Then we use the fact that we know what sine of y is. Sine of y has to be x. So this tells me that cosine of y has to be the square root of 1 minus, instead of sine of y squared, we would write x squared. Okay? And so that's where it really comes from, is from that substitution. But that is using the Pythagorean identity more directly. In the back substitution, what I want you to do is see visually why and how that works, how we can use triangles for this. Okay, so let's go through this. It says to determine the derivatives of inverse trigonometric functions, we will use implicit differentiation and the definition of an inverse function. For example, we wish to find the derivative of y, which again in this book we're going to call it arc sine. You might have seen it as sine to the negative 1, inverse sine, so we're just going to call it arc sine in this case. It says to do this, we use the definition of an inverse function. Y equals arc sine of x if and only if sine of y equals x. So that's the idea, is if you wanted to find the derivative of y equals arc sine of x, what you're going to do is take the sine of both sides. And if you take the sine of both sides, on the left you would have sine of y, and on the right you would have the sine of the inverse sine of x. Well, that's just, by definition, x. The inverse sine of, or the sine of the inverse sine of x is just x. So what they did was they took the sine of both sides and they ended up with sine of y equals x. So it says instead of differentiating the explicit function, which would be the y equals arc sine of x, you're going to differentiate the implicit function, which would be sine of y equals x. Okay? So if we have sine of y equals x, remember y here is an angle and x here is a ratio. So really you have sine of y equals x, which is x over 1. So they're using the fact that y is the angle, and if you remember, sine is opposite over hypotenuse, so they use the opposite over the hypotenuse, x over 1. So that's where they're getting that. And then what they did was they found the remaining side of the triangle using the Pythagorean identity. So you have that, I'm just going to call this side A. It doesn't really matter what we call it. Okay, let me use a different color. I'll call this side A. So what they used is the fact that the short side x squared plus the other short side a squared had to equal 1 squared, which is just 1, right? So that tells them that a squared has to equal 1 minus x squared. So a has to equal the square root of 1 minus x squared. So that's how they solve for that remaining side of the triangle that you see right there, is just by using the Pythagorean theorem on a 90-degree triangle. Okay? So it says now we use implicit differentiation. They do exactly what we did right here. They took the derivative of both sides. They ended up with y prime equals 1 over cosine of y. But we did the blue math over here, which was the Pythagorean identity, which works. What they're doing is using now the triangle. So let's think about cosine of y. Remember, y is an angle. Cosine is the adjacent over the hypotenuse. So they're saying it's the square root of 1 minus x squared over 1 and substituting it in that way. It is the exact same thing as we did in the previous section using the Pythagorean identity with substitution, with back substitution for sine of y. Exact same thing, they're just visually using a triangle with the missing side to figure that out. So what did we end up with? We ended up with y prime, which remember y prime is the derivative of arc sine of x. We ended up with 1 over the square root of 1 minus x squared. So that's a lot just to show the derivative of the inverse sine of x. A lot to show that, okay? Two different ways you can do it. You can do it exactly as we did it with the blue math last time, or you could do it the new way with the triangle that they used, finding the missing side of the triangle. Exact same thing. It's going to get you the same answer both times. So it says we can use similar techniques with the remaining 5 trigonometric functions and the chain rule to prove the following derivatives. Well, I know if I don't do it with you, you're not going to do it. So I'm going to do another one with you. Let's say we wanted to find the derivative. So let's say we have y equals, let me use black here, y equals the arc cosine of x. In other words, we want to find the derivative of the arc cosine of x. Well, here's what we know. If y equals the arc cosine of x, then take the cosine of both sides. If we did that, we would have the cosine of y equals, well, then it would be the cosine of the arc cosine of x. The cosine and arc cosine cancel out, so it would just be x right there. So now the idea is differentiate both sides of this with respect to x. Okay? So what's the derivative of cosine of y? The derivative of cosine of y using the chain rule, notice your variables don't match, would be negative sine of y times y prime. And the derivative with respect to x of x is simply 1. Divide both sides by negative sine of y. And let's see what we have. I'm ending up with y prime equals 1, or negative 1 over sine of y. That's great. Let's go back to our Pythagorean theorem. Think about sine squared y plus cosine squared y equals 1, right? Well, now instead of solving for cosine, let's solve for sine. So we do sine squared of y is going to be 1 minus cosine squared of y. We're going to take the square root of both sides, and we'd have the sine of y equals the square root of 1 minus cosine squared of y. But now, again, we're going to go and look, and we know that when you have cosine of y, we can substitute that in with an x. Cosine of y, according to the original problem, is an x. So what do we have? We would have, come in here, this would be equal to negative 1 over, and then instead of sine of y, well, let me go back up here. We would have sine of y equals the square root of 1 minus x squared, if you're with me, because the cosine of y is just x right there. And now you want to go back and plug it in here to the actual derivative, negative 1 over sine of y. Well, we know what sine of y is. It's the square root of 1. Sorry, let me do this in black. The square root of 1 minus x squared. So that tells me, we just found out that the derivative with respect to x of arc cosine, the inverse cosine of x, is equal to negative 1 of the square root of 1 minus x squared. I want you to do the same thing for arc tangent. Let's try doing the same thing for arc tangent. Let's see what we would get. So if I wanted to say y equals arc tangent of x, and I want to find the derivative of arc tangent of x. Well, this is if and only if we take the tangent of both sides. So this would be the tangent of y would have to equal, well, the tangent of the arc tangent, those cancel out. You would end up with just x, right? So now what do? We take the derivative with respect to x of both sides of this equation. So what's the derivative of tangent? Well, the derivative of tangent of y is secant squared of y, and then remember that's times y prime, right? Derivative with respect to x is just a 1. Solving for y prime, we divide both sides by secant squared of y. And we end up with y prime equals 1 over secant squared of y. So what's the idea? We need to find out what secant of y is. So if you remember, you have sine squared y plus cosine squared y equals 1. We need the one that gives us secant. And to get secant is really 1 over cosine, right? So what I do is I divide each one of these by cosine squared of y. And when I do that, what I have is tangent squared of y. Sine over cosine is tangent squared, plus cosine squared over cosine squared is 1. And on the right-hand side, I have secant squared of y. So that's my Pythagorean identity with secant squared. And again, I need to solve for secant squared. Well, I've already done it, haven't I? Isn't secant squared of y equal to 1 plus tangent squared of y? But let's go back here. We know that tangent of y is equal to x. Tangent of y is equal to x. So tangent squared would really be x squared. So tangent squared of y is really x squared. So we have x squared plus 1 would be secant squared of y. So now look, I can go back to my derivative and substitute in for secant squared of y. So this would be y prime equals 1 over x squared plus 1. So what did we just do? We just found out the derivative with respect to x of arc cotangent of x equals 1 over x squared plus 1. Okay? We could do the same thing with, oh, sorry, that's arc tangent. I said that wrong. Give me a second. Let me go in there. The derivative with respect to x of arc tangent of x is 1 over x squared plus 1. We could do the same thing with arc cotangent, exact same thing. Gets a little more tricky when you try to do secant and cosecant. Yes, you can still do the same thing, but it gets a little uglier, and you kind of need to work with it a little more. But we have proven 3 of the rules that I want you to know. I want you to make sure that you do know these rules. You understand how we prove those. There is a large possibility that I could have you prove one of the 3 of those on the test. So prove the derivative of arc sine of x is 1 over the square root of 1 minus x squared. Prove or show that the derivative of arc cosine of x is negative 1 over the square root of 1 minus x squared. Again, I don't care if you use the triangle to find the missing side, which is the same as the math that we did. You just have to make sure you substitute back in that original problem and get it all in terms of x's. So 3 different proofs of it right there for you, possibly one of those on the test.